back, over.
Hey, Houston, we've had a problem here.
Can say again, please.
Houston, we've had a problem.
One of the many reasons astronauts on the moon had to wear spacesuits is the wide variation in temperatures, from extremely high equatorial temperatures of 121 degrees Celsius in daylight, then a huge drop to minus 133 degrees Celsius after nightfall. But why don't we get the same wide temperature variations on Earth? Because the Earth's key systems help keep the conditions on Earth more stable and resist major changes, just as spacesuits do on the moon. The spacesuits kept the astronauts within a safe operating zone. The Earth systems keep us within a safe operating zone here on Earth. And the boundaries that keep us safe are called the planetary boundaries. However, some of the key stabilising systems on Earth are now at risk, and we've crossed out of the safe operating zone in most of the planetary boundaries. This increases risk. One of those 9 key planetary boundaries is climate change.
The planetary boundaries are about preserving the stability, resilience and habitability of the Earth. But what do we mean by a stable, resilient or habitable Earth system? So for us, a stable Earth system is one where certain parameters or living conditions are always occurring within certain ranges. We also want a resilient Earth system, meaning that it is good if the Earth itself is able to withstand external pressures, like we are doing right now. And last, of course, we want a habitable Earth system. That is an Earth system that can provide, for example, freshwater recycling for us, that provides us with temperature ranges that we and other living organisms feel comfortable with, that provides the nutrients that plants and humans need to grow, and other things.
Comparing the Moon and Earth, one of several reasons why the Earth's temperature is warmer on average than the Moon is that greenhouse gases on Earth, such as water vapour and carbon dioxide, are gases that slow down energy loss to space.
There are actually quite a few different definitions for what climate is. Most importantly is when you go outside on any single day and you experience either sunshine, cloudy weather or rainfall, that is not climate, that is weather. But what determines the weather on average, so the weather that we experience over long time periods, is the climate. So one way to define climate is actually to look at all the weather variables like precipitation, rainfall, temperature and so on, and average them over 30 years and saying, okay, this is the state of the climate. But climate is actually even more than that. As climate scientists, we say climate is the state of the whole climate system. And that also includes the ocean and how much heat and carbon is stored in the ocean, the soils, what is their temperature. It also includes the hydrosphere, so the whole water, freshwater cycles, the cryosphere, that is the state of the ice sheets and the sea ice, and much more. So climate is not just what we experience and see in the atmosphere, but it really encompasses all the different subsystems of the Earth.
When the incoming energy from the Sun reaches the Earth, some of it is reflected away by low altitude clouds, snow and ice. But the rest reaches the Earth's surface and warms up the land and particularly the oceans. If the processes of incoming energy and outgoing energy don't balance out, then the Earth's temperature changes. One way to disturb that balance is by adding greenhouse gases such as carbon dioxide. This results in less energy escaping back out into space, and as a result, the temperature rises. To give you an idea of how much additional heat energy we've added to the oceans via our greenhouse gas emissions, we can use the Saturn V rocket that took humans to the moon. We now know that the total extra energy added to the oceans since 1955 is the same amount of energy as you would get from launching 7 billion Saturn V rockets. But how much is 7 billion? Well, 7 billion seconds is roughly 220 years. Our emissions have pushed us towards and then over a key planetary boundary, causing a rapid rise in global temperatures and significant impacts on climate and Earth's key systems. Today, the primary cause of the rise in emissions of greenhouse gases is the production and burning of fossil fuels, such as coal, oil and gas. and to a lesser extent our land use change. In fact, the emissions from human activities now exceed volcanic carbon dioxide emissions by more than 80 times. The current rate of change is both historically rapid and causing significant harm.
The main consequences of global warming include, next to the general rise in global temperatures, an increase in heat extremes, in precipitation or in extreme precipitation events, that is a lot of more rainfall. At the same time, contrary to that, we also see an increase in droughts, so dry extremes. This really depends on where on Earth you're living. We also see an increase in the sea level globally, but regionally this can also be quite severe. And overall, we have increased pressure on basically all living organisms on Earth, with many of them having to migrate due to that.
Of course, nature is not only under pressure from climate change. Loss of species, water and land use change have opened cracks in the system, and that in turn weakens Earth's ability to absorb our climate impacts. So as you can see, climate change and specifically the rate of change make it hard to adapt to. Fortunately, we know how to bring us back into the safe operating zone on climate change. We need to cut emissions of greenhouse gases, replace the burning of fossil fuels for energy, protect the most vulnerable, and help nature bring stability back by protecting nature's ability to reduce carbon dioxide back to safer levels. The planetary boundaries are interconnected, so reducing the risk in one can reduce the risk in others. You can find out more about the planetary boundaries in this ongoing video series, including more contributions from key scientists and experiments you can try. Thanks for watching and see you again soon.
9, ignition sequence start. 6, 5, 4, 3, 2,